Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and in this module we are trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within this module currently we are on the last topic, that is the sixth topic, CPU scheduling policy, right? So as you know, within this topic, we are trying to study the different scheduling policies that exist. Basically, scheduling policies are algorithms that the CPU scheduler uses to decide which process will run next on the CPU, right? And depending on different types of systems, there are different types of algorithms, and we are currently studying the algorithms for batch systems in the previous few videos, right? So we talked about the first come first serve algorithm, then we looked at the shortest job first, and both of them have some drawbacks, right? So in this video we are going to look at an alternative algorithm, that is shortest remaining time first. Again, this is an algorithm for batch systems, right? So let's see how does this algorithm work, and how what is its performance as compared to the previous algorithms that we have studied, right? So without further ado, let's get started. So let us start the discussion from this slide. Basically, we have been looking at the scheduling policies that are used in batch systems, right? And in batch systems, the goal is to optimize for turnaround time, throughput, right? So we want low turnaround time, low waiting time, and a high throughput for the jobs that are executed in batch systems. And in batch systems, we have been looking at quite a few algorithms, right? We started with the first come, first serve. It was a simple algorithm, but again, it suffered from the convoy effect. Then we looked at the alternative, that is shortest job first. It looked like that it solved the problem of convoy effect, but not really. It also suffers from convoy effect if all the jobs do not come at the same time. Basically, when larger jobs come before the shorter ones, right? Otherwise, if all jobs come at the same time, then we can prove that the shortest job first is the optimal algorithm for batch systems where we are optimizing for throughput, turnaround time, and waiting time. So the proof for this, I will do that in the next video, right? So as we saw that yes, shortest job first, although optimal, the optimality is under certain conditions or certain assumptions that all the jobs should come at the same time. So now let's look at the other alternative, that is shortest remaining time first, and see whether it can do better in some ways to shortest job first, because we have already said that shortest job first is optimal, the most optimal, but there is a condition, there is a star mark that all jobs should arrive at the same time. Let's see that can shortest remaining time first solve that issue, right? So we'll start with an example. We'll look at what was the problem with the shortest job first, and using that problem, we'll try to solve it using the shortest remaining time first, right? So we will again take a hypothetical system, right? In this system, there are three processes, P1, P2, and P3. And you can see the arrival times and the burst times I have mentioned in this table. Let's just assume that all of these times are in milliseconds. So as always, there is an assumption whenever we are discussing these scheduling policies. The assumption is that the runtime of each jobs is known, and all jobs only use the CPU, that is they perform no IO, right? I have been calling it out in all of the previous videos because these are important assumptions, right? Because in reality, in real life, these assumptions do not hold true. We are doing, since we're just studying these policies for the sake of study, we are making this assumption. While designing real policies, these assumptions are relaxed, and moreover, real policies are much more complex. But nonetheless, to understand those policies, we have to go step by step through these simple policies, right? So in reality, the runtime of the job will never be known, right? And also the processes or the programs that we run will have a CPU IO burst cycle, right? So that was all for the assumptions. Let's quickly move to the example, right? So let's start running these processes, and from that we will make the Gantt chart, right? So as you can see, at time 0, at t is equals to 0, process P1 arrives in the system, right? And it is a long job. It is a job which has a high burst time, that is 80 milliseconds, whereas the other jobs, that is P2 and P3, have comparatively very small burst time, that is 10 milliseconds. Now here is where the problem occurs. We are just to be just to be clear, we are executing these processes under the shortest job first, right? So you can see all jobs have not arrived at the same time, first of all. And this is where the shortest job first does not guarantee optimality. And to be specific, in this particular example, the longer job has arrived first, right? And so since at t is equals to 0, P1 is the only process, that is what will get scheduled, right? So at t is equals to 10, when the other two shorter processes arrive. So P1 is already scheduled on the CPU. This is where the problem arises, because shortest job first is a non-preemptive policy. So since process P1 is already scheduled, we cannot do much. It will execute till completion. And these shorter jobs, that is P2 and P3, although they are quite small, comparatively much smaller than P1, right? P1 has a burst time of 80 and P2 and P3 have a burst time of 10. Nonetheless, they will have to wait, right? They will have to wait for the longer job to finish, because shortest job first is a non-preemptive policy, right? And the problem here is that the longer job arrived before the shorter jobs. So now P1 completes, and then both P2 and P3 actually have the same burst times. They arrived at the same, so both their arrival times as well as the burst times are same. So out of P2 and P3, which one will go first? So just to break the tie, let's just assume that the process with the lower process ID goes first, right? So P2 will go first, like before P3, and then finally P3 will execute. Like you can see, we have the convoy effect, right? So we saw that convoy effect can arise in first come first serve. It can arise in shortest job first. Whenever the policy is non-preemptive and a longer job arrives before, it gets scheduled before, whether it is first come first serve or shortest job first, whatever is the policy, if it is non-preemptive and a longer job is scheduled before the shorter one, there will be convoy effect, right? And the result of the convoy effect is that the shorter jobs will have a very high turnaround time, and which will kind of impact the average or the overall turnaround time as well as the waiting time. So let's just quickly calculate the numbers. So for this example, these are the completion times. So from completion time and arrival time, we can calculate the turnaround time, right? So turnaround time, just to recall, is the total time spent by any process in the system, and it can be calculated using this simple formula, that is completion time minus arrival time. So the total time from the arrival of the process to the departure makes up the turnaround time. So just subtracting the completion time minus arrival time, you get the turnaround time. And from this turnaround time, we can get the waiting time, because the turnaround time is composed of two components. One is the burst time and the other is the waiting time. So if you look at the life of a process, there are two activities that it does. Either it will be executing instructions on the CPU, right? So that is what makes up the burst time. Otherwise, if it is not executing, then it will be waiting for the CPU to be assigned to it. That is what is the waiting time. So we want both the waiting time as well as the turnaround time to be low. So a job should come, it should quickly get the CPU and then quickly depart from the system. That is what a ideal batch system would look like. So we are trying to optimize for both the turnaround time and the waiting time. So waiting time we can calculate using this formula. That is, whatever time the process it is not executing, that is turnaround time minus burst time, is the waiting time. And from here you can get the average turnaround time. So you can look at this. So the average turnaround time is 83.33 and the waiting time, the average waiting time is 50. So you can see jobs, these smaller jobs, they just have 10 milliseconds of execution. And for these this 10 milliseconds of execution, they have to wait 80 milliseconds. P2 has to wait 80 milliseconds for doing 10 seconds of work. P3 has to wait 90 seconds. Sorry, not this is the turnaround time. So this is the waiting time. Sorry, P2 has to wait 70 milliseconds to get 10 milliseconds of job done, and P3, although it only executes for 10 milliseconds, has to wait for 80. And overall, the turnaround time, the overall time spent by the process is also very high, right? So this is the issue, right? So we saw that the shortest job first still has the convoy effect problem. So now let's see whether shortest remaining time first, the newer policy, solves this problem or not. So how does the shortest remaining time first work? So shortest remaining time first, or SRTF for short, right, is a preemptive scheduling algorithm. So this is the first preemptive algorithm that we are talking about for batch systems. All the previous ones, that is FCFS and SJF, both of them were non-preemptive. So this is a preemptive policy, which is very important to note. And what does it do? It selects the process with the shortest remaining execution time, not the shortest burst time, shortest remaining execution time, right? So we have to understand what is this remaining execution time. We'll see this with examples, right? So two important points. SRTF is a preemptive solution, preemptive algorithm, and it basically prioritizes processes which have the least execution time left, right? So let's again take this example, the same example where the shortest job first suffered from convoy effect, right? Let's take the same example and execute that via the SRTF. So in SRTF, we'll again make the Gantt chart, right? So process P1 arrives first at t is equals to 0, just like previous time. And it is the longer job. It has a 80 milliseconds burst time. and it will get scheduled on the CPU, because at t is equals to 0, there is no other job in the system. At t is equals to 0, it is only the process P1 which is there in the system. So there is not much of a choice. So the scheduler will schedule process P1 to be executed on the CPU. Then at t is equals to 10, the two remaining processes P2 and P3 arrive. And now at t is equals to 10, we have to notice what has happened with P1. With P1, out of 80 milliseconds of work that was planned, right? Basically, we have said that P1 will require 80 milliseconds of execution time, right? And so it has already executed for 10 milliseconds. So the remaining time that is left for execution is 70, right? From 80, 10 is already done. So the basically this means that P1 now needs 70 milliseconds more of execution. So this is the remaining time that we should be aware of, right? We said in the definition of SRTF that SRTF, or shortest remaining time first, will prioritize the process which has the shortest remaining time, right? So 80 is the total burst time and 70 is the remaining time. So now we have to be careful and calculate the remaining time as well. So now at t is equals to 10, the scenario is like this. There are three processes in the system, all of them ready to execute. You can see P1, P2, P3, all of them are in the ready queue, right? P1 has a remaining burst time of 70, and P2 and P3, they have a remaining burst time of 10. Basically, P2 and P3 have not yet started execution. So the remaining time and the total burst time is the same, which is 10. So now which one will get picked, right? So as we said, the shortest remaining time will be prioritized. So here, the shortest remaining time is 10 milliseconds. So both P2 and P3 have shorter remaining burst times than P1. So P1 will not be executed further. It will be preempted, right? So this is where the difference lies between SRTF and SJF. SRTF is basically a preemptive version of shortest job first, right? It is still prioritizing shortest jobs, and it is kind of doing it more aggressively. It is checking at whenever a new process comes in the system, right? Or whenever a process leaves the system, whenever there is a chance to do scheduling, it basically analyzes or re-evaluates for the shortest job, and for that it takes the shortest remaining time into account. So this is a very important point, that shortest remaining time first is a preemptive version of shortest job first only, right? So now out of P2 and P3, both are equally likely candidate to get executed, since they have the same arrival time and the same burst, shortest, like same remaining time. We'll just allow P2 to execute since it has a lower process ID, right? So P2 executes, and you can see after another 10 milliseconds, that is at t is equals to 20, P2 is done. Its remaining time is now 0. It does not require any further CPU time. P2 has left the system, right, at t is equals to 20. Then at t is equals to 20, again the scheduler will re-evaluate the situation. Now there are two processes remaining in the system, P1 with a remaining burst time of 70 and P3 with a remaining burst time of 10. So which one will get picked? Obviously the one which is shorter. So P3 with a shorter remaining burst time, that is 10, will picked as compared to P1. So P3 will execute from 20 to 30 milliseconds. At t is equals to 30, P3 also departs. You can see the remaining time for P3 is now 0, right? And when all of the jobs, basically P2 and P3, have left the system, the only remaining job is P1, and that will now get to execute. So P1 was preempted at t is equals to 10, remember? So now P1 will complete its execution, and P1 completes at 100. So this is how the shortest remaining time first algorithm behaves differently than shortest job first. It does preemption, right? And it prioritizes shorter remaining time compared to the shortest total burst time, right? So preemption is important, and the remaining time also. So let's calculate the turnaround time and the waiting time using the shortest remaining time first algorithm, right? So we calculated the completion time in the previous slide. So we will calculate the turnaround time using the simple formula, completion time minus arrival time. And then from that turnaround time, we'll calculate the waiting time by subtracting the burst time. Let's quickly calculate the average and then compare it with the shortest job first. You can see there is a significant drop in the turnaround time. So let us compare the metrics for both of these algorithms. So you can see for the same example, right? Same number of processes and the same arrival time and burst time. These three columns are identical. For the same scenario, right? How does the shortest remaining time first and shortest job first behave differently, right? So you can see that SRTF has a much smaller average turnaround time, like almost half, right? And similarly, the waiting time is like 1/5 of the waiting time for average waiting time for SJF, right? So for this example, we saw that SJF suffered from convoy effect, right? But that is kind of solved by SRTF. And how does this happen? Because SRTF, the main advantage of SRTF is that it is a preemptive policy, right? So convoy effect was happening because a longer job arrived first and it got scheduled. And once it got scheduled, since we were following a non preemptive policy, we were not able to schedule the shorter jobs because they arrived later when the longer job has already been scheduled. But that is not the case with SRTF. We saw that in SRTF, whenever a shorter job comes, right? Let me go back up the previous slides. Whenever the shorter jobs comes, right? At t is equals to 10 when P2 and P3 arrived, right? Even when the longer job, that is P1, was already scheduled, P1 got preempted and the shorter jobs got to execute. So this preemption is where the difference happens, and that is why SRTF is able to avoid the convoy effect and achieve a lower turnaround time as well as the waiting time, right? So in the previous video, when we discussed shortest job first, we said that SJF is an optimal policy under the following conditions. We listed three conditions. The goal is to optimize the turnaround time. So we were talking about batch systems where the goal is to optimize the turnaround time, right? And the burst time of the jobs is known. This is a very important consideration assumption, because all of the policies that we are trying to implement, we already know the burst times, right? When we say shortest job, for that we have to know shortest of what? We have to know all the burst times, right? And the last assumption was that all jobs arrive at the same time. When all these three conditions are there, then shortest job is the optimal policy. Basically, when I say optimal, I mean that no other policy will perform better than shortest job first in this under this scenario, right? Where all three conditions are fulfilled. Now, since we said that shortest remaining time first is just a variation of shortest job first, that is, it is just a preemptive variation. Shortest job first is also trying to do the same thing. It's just that it is non-preemptive, whereas shortest remaining time first is a preemptive version of shortest job first. It is taking into the account the shortest remaining time, shortest remaining burst time. So on the same grounds, we can say that since SJF is optimal, shortest remaining time first is also an optimal policy. And in this case, the three conditions I have just taken from the previous slide only. This last condition was also not required, right? All jobs should arrive at the same time. This was the condition that was required in the case of shortest job first for it to behave in an optimal manner. But that is not the case with shortest remaining time first. Even when this condition is not fulfilled, that is, the jobs arrive at different times, and in real life, this will be the case that the jobs will be arriving at different times, right? To assume that all jobs will arrive at the same time is not practical. So shortest remaining time first, or SRTF, is an optimal policy. And for this, only two conditions are required. That is, we are trying to optimize for turnaround time, right? It is optimal for optimizing turnaround time, right? When the metric is turnaround time, then shortest remaining time first gives an optimal, that is lowest turnaround time. And the burst time of the jobs should obviously be known, right? We do not require this condition that all jobs be arrive at the same time. So both of these proofs, that is the proof for the optimality of shortest job first and shortest remaining time first, we will look at in the next video, right? So let's come back again to the analogy that we have been following, and that is of a grocery store, right? So in a grocery store, when the customers have picked up their items and they have the trolleys and the baskets ready, they go to the billing counter, and in the billing counter there is a queue. Now, in what order should the grocery store process or bill these customers, right? So if we want that overall the waiting time for the customer should be minimum, then we can go for shortest job first. That is the idea behind shortest job first. In shortest job first, we were prioritizing the shortest job, that is the one with the lowest burst time. So in the case of customers, we can think of this in this way, that whoever has the lowest number of items, the one with the fewest number of fewer number of items will be prioritized first, right? And the people who have more number of items, maybe they have done their monthly shopping, they have full trolleys, then they will be built in the end, right? So here, till the previous video, that is when we were studying shortest job first, we had this assumption that when all customers come at the same time, then it makes sense to follow this policy. So now when we are following the shortest remaining time first, then in this case, even if customers with fewer items come later, and just to give you an analogy, right, this might not happen in the real life, right? Let's say there is a customer who has started billing and they have a lot of items, right? For example, this person, he has a full trolley, right? He has started billing, but let's say someone comes with just a simple, let's say one toffee. A kid comes with a toffee, then in the shortest remaining time first, under this policy, the one with fewer items will get priority. So the management will stop the billing for this person. They'll ask them to wait and then quickly bill the one with fewer items and let them go. And then they will resume the billing of the person with more number of items. You might not see this happening in real life, right? Because customers would get angry. But just to give you an analogy, this is how the shortest remaining time first works. It's a preemptive version. You can see that for the person who was already getting billed, we stopped, like basically we preempted in a way. We stopped the billing for that person since there was someone else who had fewer number of items, and they got preference over the one who was billing, and they got to bill first and they got to leave. Only after they left, then this person might get a chance to resume, under the assumption that there is no other person with fewer number of items. So this is how uh, we can apply, like how shortest remaining time first, the idea behind that policy would work in this case, right? So now you might have noticed the problem with this when we are discussing this uh, idea for shortest remaining time first in the context of this grocery store. You might see that there is a problem. What is that problem? Let us understand further with an example, right? So we'll take another example and see what is the drawback of shortest remaining time first. So let us see this example and understand what is the problem with SRTF policy, right? So you can see this example, there is a process P1, right? It has a burst time of 80 milliseconds. It starts from 0 and it is going till 80. It has not yet been scheduled. It has just arrived at t is equals to 0 in a system where we are following the SRTF policy. So let's see this example, and from this example, we'll see what is the problem with SRTF, right? So since this is the only job, that P1 is the only job at t is equals to 0, it will get scheduled, right? Now let's assume that at t is equals to 10, a shorter job, that is P2, comes. P2 has a burst time of 10 milliseconds, right? So now we know that in SRTF, whichever job has the shorter remaining time, that will get priority. So P2, since it has a shorter remaining time, that is 10 milliseconds, P1 had total burst time of 80, right? And after executing 10 for 10 milliseconds, its remaining burst time is 70. And compared to P2, which has a burst time of 10, it is more, right? So P1 will get preempted and P2 will get chance to execute on the CPU, right? In a similar way, let's say at t is equals to 20, another job comes P3, which is again has a burst time of 10, right? And if we come, so which job will get scheduled? P2 is already finished. So P1 and P3, these are the two candidates. Since P1 has a remaining burst time of 70, which is more than P3's remaining burst time, which is 10, again P1 will not get the chance, it has to wait, and P3 will be scheduled by the scheduler, right? So you can see what is happening and what I'm trying to convey. And at t is equals to 30, let's say the same thing repeats. So another shorter job comes, P4. It again has a shorter remaining burst time, that is 10 compared to 70. Again, P1 has to wait and P4 gets to execute. So the problem here is that if shorter jobs keep arriving continuously, the longer jobs will starve, right? So starvation is that the meaning of starvation is that they will not get the chance to execute on the CPU, and this could be forever. Like if the obviously this is based on the condition on a scenario that the shorter jobs keep coming, right? If there is a continuous flow of jobs which have a shorter remaining time, then the ones which have a longer remaining time will never get a chance to execute on the CPU, and they will never finish. So they are kind of getting starved. So this is the drawback of preemptive policy, right? Since so preemptive policy on the one hand is able to solve the convoy effect, that is if a longer job comes first, it is able to remove that because it's a preemptive policy in favor of some shorter jobs. On the other extreme, if it is the case that the shorter jobs keep coming, then the longer job will always get preempted, right? So there are two extremes to this scenario. In one side, we are able to solve the convoy effect by preempting a longer job which arrive before the shorter job, so that the overall waiting time, overall turnaround time is low. But in the other case, if the shorter jobs keep coming, then although the overall waiting time and the turnaround time will be optimal, but the longer job will stop, right? So this is the drawback for SRTF, right? So again, as I said, if you think of this in the context of a grocery store, if a man, for example, in this case, someone has like full trolley of items and they have started billing, if the store is following this policy that whoever has the short, like similar kind of policy like SRTF, that whoever has lesser items will be given preference. It's okay once or twice, right? Someone just comes with one item, then they're quickly billed and like they're let to go. But if this man has to wait, like every time someone comes with a lesser number of items than this man, then this is a very bad customer experience, right? No one would tolerate such an experience, right? And in reality, such kind of policies do not work, at least in this example, right? So in this grocery store example, if we keep on like prioritizing someone who has lesser number of items and do not give, like do not bill the customer with more number of items, this is again kind of unfair, right? As we said, starvation will occur, so it is kind of unfair to the longer jobs, right? They should also be given preference. So this is one drawback of this policy, that is SRTF. There are other policies which kind of try to draw like, so this is basically extreme behavior, right? On one end we are either having convoy effect, on the other extreme we have starvation. So there are policies which try to make the best of both and favor both, like favor shorter jobs but also ensure that the longer jobs do not starve, right? So this was about SRTF. So what are the pros and cons of SRTF? As we discussed, just like shortest job first, it is an optimal algorithm if the goal is to optimize turnaround time and the job lengths are known. As was the case in shortest job first, we do not have this requirement that all jobs should arrive at the same time. It is optimal when even these two conditions are true, right? So this is the advantage of SRTF. The drawback or the con is that it can cause starvation for longer jobs under the condition that there is a continuous flow of shorter jobs, right? So in that case, the longer job will keep on getting preempted in favor of the shorter jobs. So this was about SRTF. So now we are reaching the end of like the scheduling algorithms that we wanted to discuss for batch systems, right? We had discussed three major algorithms: FCFS, SJF, and SRTF, and all of these algorithms are for batch systems where the goal is to optimize for turnaround time, right? Low turnaround time, low waiting time, high throughput, right? So we discussed these three policies, and now from next video onwards, we are going to look at other systems, that is interactive systems, which work totally different from batch systems, right? So before we do that, let's just quickly summarize and compare what all the different policies that we have talked about till now, right? So these are the three policies. So first is the difference in how they work. So FCFS works basically, it prioritizes jobs based on their arrival time. Whoever comes first gets the chance to execute on the CPU. As the name suggests, first come, first serve. Shortest job first will prioritize the job which has the shortest burst time, right? This does not and this is different from SRTF will prioritize the job which has the shortest remaining burst time, not the total burst time, whereas shortest job first will take into account the total burst time. In the case of shortest remaining time first, we are always calculating, right, like how much time is remaining for each job, and whichever is the shortest remaining time first, that job will get to execute on the CPU, right? So this is how the difference between all these the working of these policies. Then about whether the algorithm is preemptive or not, the first two are non-preemptive, and as we saw, due to this they suffer from the problem of convoy effect, right? So you can see the con is that first FCFS and SJF suffer from convoy effect precisely because they are non-preemptive. If a larger job comes first and gets scheduled, then the shorter jobs will be like have to wait for a long time, and that is what is convoy effect. So this was due to non-preemptive nature of these two policies. And SRTF is preemptive in nature, right? Even if a longer job comes first, if a shorter job comes after that, then it will be given preference. So this was about SRTF, and we saw due to this preemptive nature, although we are able to solve the convoy effect problem, the drawback is that the longer job will suffer from starvation, right? It might be the case that it will never get the chance to execute on the CPU. But that is not the case with FCFS and SJF. Although there will be convoy effect, right? Although the shorter jobs will have to wait for a long time, but they definitely will get a chance to execute at some point in time, because the longer job will eventually end, right? So the shorter job, the shortest, like both of these policies will eventually allow the shorter jobs to execute. So basically there is a trade-off. If you have a non-preemptive algorithm, then there will be convoy effect, which means higher turnaround time, higher waiting time, but there is no starvation. There is a guarantee that at some point in time the job will definitely get to execute. It might have to wait, but it will get to execute. Whereas in SRTF, the convoy effect is solved, right? The shorter jobs do not have to wait; they will quickly get executed. So although the overall turnaround time and waiting time will be optimal, but the longer job will get starved, right? So this is the trade-off for between these algorithms. And finally, the advantage, let's talk about the advantage. We already talked about the cons. The advantage of FCFS is that it is very simple and easy to implement, right? Then the other two algorithms is that SJF is optimal, right? For batch systems, it has three conditions for optimality. We are basically optimizing for turnaround time, right? The burst time of the jobs is known and all jobs arrive at the same time. Similarly, SRTF is also optimal. It's just that this condition is relaxed. That is, all jobs need not arrive at the same time. If we know the jobs, if we know the burst times of all the jobs, and if our goal is to optimize for turnaround time, then SRTF is optimal, right? So guys, this was a brief comparison of all the policies. We are done with the scheduling policies for batch systems. We talked about three policies: FCFS, SJF, and SRTF, right? So guys, this was it for this video. Thank you very much for watching. I will see you in the next video. Thank you.